Hello, everybody, and thank you for joining us for our October webinar. Today, we're going to be talking about pushing the envelope in existing multifamily. My name is Matthew Mills, and I'm an energy advisor on the OHCS Multifamily Energy Program. And today, we have with us Nick Young from the Association for Energy Affordability, and he's going to be presenting for us. Just a few housekeeping notes and instructions on GoToWebinar. Today's webinar will be recorded and available on the program website within a few days. All attendees are currently in listen-only mode, so if you'd like to ask a question, please ask the question in the question box on the GoToWebinar panel that you'll see on the right. We'll do our best to answer these questions in the order that they're received. And at the end of the training, we'll open the audio line for questions if you want to speak in person. So if you want to participate in that discussion, just please enter your audio pin located at the center of your panel on the screen, and then raise your hand in the meeting panel so I can unmute you. Just a reminder, we have more trainings coming up. We have a few months of break, so our next one will be on Thursday, January 23rd in 2020. It's going to be at noon, and we're going to be talking about ductless heat pumps and their controls. So please feel free to register for that. It's up online on GoToWebinar online, but also check out our monthly newsletter if you haven't already registered to receive that monthly. We will have updates and our webinars will be introduced there as well. So just a brief introduction of Nick Young, who will speak in just a moment, but Nick Young with the Association for Energy Affordability will deliver this training. And as a trainer, Nick enjoys helping demystify technical concepts and giving people the tools and confidence to use different approaches that can improve buildings and reduce environmental impacts. He firmly believes that strategies to address the housing and climate crisis are complementary and not competing. AEA is dedicated to preserving safe, healthy, and affordable housing and reducing climate impacts through energy efficiency and building decarbonization. They are very happy to partner with programs like ORMEP that share those goals. So as a quick overview of why we're here is the ORMEP incentivizes energy efficiency measures that result in electric savings. So when we're talking about existing multifamily, there's a lot of different ways that you can achieve electric savings that we will then incentivize. So we wanted to give an overview through this training of different methods and things we've seen in the past. And with that, I will hand it over to Nick, and he can take us through the agenda.
All right, thanks, Matthew. Is my audio coming through?
Sounds great.
Okay, great. Yeah, so we're going to cover a few different topics on this webinar. We're going to start with envelope basics, touch on air sealing, insulation, windows, and then finally a bit on ventilation. So let's jump into envelope basics. The building envelope is really there to control the movement of different things. First of all, water. Right? We want to keep water out of our building. The envelope also controls fire. We want to keep fire from spreading within our building or from one building to the next or from outside to inside. So the envelope controls fire. We want our envelope to control air movement. We don't want lots of air leakage. The envelope controls heat movement, either into or out of our building. The envelope also controls light. So opaque building components stop light, but we have transparent or translucent envelope components called windows and sometimes doors that have glass in them. And those allow more or less light. And then also sound. Sound can move into or out of our building through the envelope. And what we do with our envelope can affect how quiet it is inside of the building. So a lot of times we focus on just heat or just air, but it's important to keep in when we're talking about energy. But it's important to keep in mind that the envelope is doing a whole bunch of different things. And so every component is really serving multiple purposes. And building envelopes over time have evolved. On the left, we have one of the oldest still standing buildings from 1200 BC, just a pile of rocks. And then on the right, we have a newer building that's going up in San Francisco right now with a much more complicated building envelope. But ultimately, the one on the left is trying to do very similar things to the one on the right. It's controlling the movement of those things that we talked about. You know, uh, one might be more effective at doing that than the other, but also the one on the left is quite simple and quite durable. I think if we were to look 3,000 years from now and nobody touched it, that tower on the right probably wouldn't be around anymore, but the one on the left might still be. So let's jump into our first main topic. And a phrase that folks have probably heard in building science is build tight, ventilate right. This is a very simple way to think about how we can make our building envelopes better. And we're going to start by talking about how we build tight. We do that through air sealing. So why bother building airtight? Well, a few reasons. First of all, comfort. An airtight building has reduced drafts and fewer cold or hot spots in the home because you don't have air moving willy-nilly in and out of the building. Airtight buildings are more durable. If we have airtight, vapor-permeable envelopes, they reduce potential for unwanted moisture buildup inside the assembly that could lead to rot or mold or deterioration. And finally, energy efficiency, right? Some folks might lead with this. I think this is definitely a benefit of airtight construction, but it's not the only one. But we can indeed save energy and save money by building airtight and reducing the energy that's just wasted through air leakage. So if we want to assess air leakage in an existing building, how can we try to do that? We could start with a visual inspection. And air leakage in buildings tends to be around penetrations. Places such as doors, windows, ductwork that moves or that passes from one space to another space that's supposed to be separated. So for example, if you have a multifamily building and you have ductwork going from the hallway into a unit or vice versa, electrical outlets or switches, and also pipe penetrations, which are often underneath sinks. Around all of these often are locations of air leakage. Something important to note when we're doing a visual assessment, particularly of an existing building for air leakage or for potential air leakage, is that insulation materials does not stop air movement. So oftentimes we will see these gaps and openings that have just been stuffed with insulation, either rock wool or fiberglass insulation. This can be effective for stopping the spread of fire. And so there are actually locations where we have to put insulation in a gap for fire stopping, but this still allows air leakage. So just because you see something in there does not mean that it's airtight. Airtight materials are things like wood, drywall, caulk, foam sealants, and some tapes. Not even all tapes are airtight. So if you don't see an airtight material, you may have air leakage in that location. But we can go one step further than just doing a visual inspection of air leakage. We can actually test for it. So to measure air tightness, we can use a blower door test. These are usually performed by a HERS rater or a BPI building analyst. And what this does is it establishes a baseline against which we can measure improvement. So you pressurize or depressurize the building, establish how tight the building is, how much air leakage there is at a particular pressure. You can also, when the building is pressurized or depressurized, you can do some visual verification of air leakage using things like a smoke pen or sometimes just putting your hand against the wall in areas where you might have air leakage. You can actually feel the air movement. And so you can, with a blower door test, you can test a whole building. In the case of a single family home, that's generally how it's done. Or you can test for compartmentalization of individual dwelling units in a multifamily building. So compartmentalization is pretty commonly done in multifamily. Whole building testing is not as commonly done, but it is growing in popularity. But you do need to have a building with sort of interior corridors and like a garden style building with exterior walkways. You wouldn't be able to test by a whole building. You'd only be able to do compartmentalization testing on that. So how do we actually go about improving the air tightness in an existing building or in a rehab situation? The good news is that a lot of envelope upgrades that you may already be doing will likely tighten the envelope somewhat. So replacing old leaky windows will definitely make the envelope tighter. Adding insulation in some cases will make the envelope tighter. Depends on what kind of insulation. Dense pack insulation does tend to reduce air leakage. But we would recommend including specific air sealing measures in any insulation scope. So if you have an old building with an uninsulated or poorly insulated attic, make sure that it's air sealed before it's insulated. So if you're going to add more insulation or you're going to insulate it for the first time, make sure that it's air sealed first and then insulated. Air sealing can be tricky because often many trades are involved in sealing of penetrations. On a lot of projects, the plumber is in charge of sealing the plumbing penetrations. The HVAC installer is in charge of sealing the HVAC penetrations. Electrical is in charge of sealing the electrical penetrations. So there's often not one trade that's responsible for air tightness, but it's all important. So best practice for existing buildings is to start a project with a blower door test for your rehab project, to test it before and then also test it again after the work is completed to understand the impacts of the scope that you're doing. So it may be that the work that you just sort of normally do during a rehab already does a lot to improve air tightness, or it may be that it really doesn't. But the only way to know is to actually test your projects. So as a starting point, if air tightness isn't something that's usually in your standard scope, we would suggest that on your next project, start by testing before and testing after and seeing how the air leakage in the unit changes, and then doing some diagnostic testing to see if you can find where the leaks are and how you might improve them over time. Any questions on air leakage?
Yeah, we do have one question. I think it's a pretty good one. Is if somebody was interested in having a blower door test done, how would they find a contractor to do that?
That's a good question. I am familiar with the registry of HERS raters in California, but I'm not familiar with the specific, like where online you would find HERS raters or BPI building analysts in Oregon. Matthew, maybe someone from your team could follow up on that.
Yeah. So I think what you just said is having the HERS registry, which is just right online, is a great idea. And then also our program team has a list of energy consultants that we work closely with. That would be a really good start. So anybody that's listening that has interest in having an energy consultant on board, you can just reach out to us and we can provide a few names for you.
Awesome.
Thanks.
Okay.
And that's it.
Okie doke, great. So let's move on to insulation. So once we have an airtight building, we need to make sure that it's well insulated. And there are a few different common insulation materials. Fiberglass, cellulose, rock wool is becoming increasingly popular, as well as some foam products. There are foam board products like EPS, XPS, and polyiso, as well as spray foam, both open cell and closed cell. And one thing to think about when we're considering insulation products is what's in them. If you notice, there's one picture in here where the person is having to wear a lot of personal protective equipment to apply that material. And so not all insulation and not all building products are created equal when it comes to their health impacts, both on the installers and potentially on residents. So there are some good resources out there to help us choose healthy building materials. Some materials are pretty benign and others have been linked to negative health outcomes, and so it's important to be informed about what we're putting in our buildings. So I'd recommend that everyone, if you haven't already, take a look at a guide to healthier upgrade materials from Energy Efficiency for All. And they've got some great information in there to help you select materials that will both perform in terms of insulation and air sealing, but also not pose other issues that you might not be aware of. So when we're insulating a building, generally we start by insulating the top of the building, right? The first step is to put a hat on it. And the tops of buildings come in a few flavors. Some are attics. If we're insulating an attic, you would want to, like I mentioned before, air seal it first and then blow in fiberglass or cellulose insulation. Bats tend to be a poor choice in attics, because to get sufficient R value, the bat is going to usually be taller than the framing that it's installed between. And so you're going to have gaps and voids. So like if you look at this picture here with these, we have a truss system. If they had installed bats, and in fact they wanted to install bats on this project, but we told them they wouldn't meet the insulation standard because they would have had gaps. The bat would have been sort of to this edge, but then there would have been a gap here between these framing members. And everywhere there's a framing member, they would have had gaps. So generally in attics, especially if you're going for a higher R value, blown in insulation is a better choice. If you have a cathedral or flat roof, you could, for an existing building projects, you could add rigid insulation when you're replacing the roof. You know, depending on the circumstances, you may need to add sloping for drainage of the roof. So once we've insulated the top, let's move to the bottom of the building. Bottom of the building can be tricky in existing buildings, and what works depends on your floor framing. I mean, if you have a slab on grade, then you just can't, there's nothing you can do. You got concrete on the ground. You can't insulate it. When you do have some sort of raised floor that you can get to, you have a few different options depending on what your framing is like. If you have your floors framed at 16 on center, you could do friction fit or stapled bats, or you could do blown in insulation with netting between them. What if, on the other hand, you have a situation like we see in this photo? It goes by a variety of names. We call it post and beam, where here we have really long spans. Like this is about 36 inches of just clear open area. No bat is going to be able to be friction fit in this space. It's just not possible. So what do you do here? Do you put in netting and blow it in? And even that, 36 inches is a pretty long span. Do you use spray foam? Like this is pretty tight. It's a very difficult location to install spray foam. Spray foam may have some other concerns. Some folks don't like it. Frankly, this is just a very challenging situation, and it really depends on the contractor and what you're comfortable with. We don't have like a nailed shut every time easy win solution for this. It's kind of it's a tough one. If you're dealing with garage ceilings that are concrete, where you have apartments above the garage, you're usually going to have to use some sort of fireproof material. It might be some sort of foam or rigid rock wool or rigid foam could be installed if you have a nice smooth garage ceiling surface. So that's the top and the bottom of the building. What about the sides? So in some older buildings, we might not have wall insulation in our framed walls. So if we're removing drywall, or maybe we're removing the sheathing and the cladding from the outside, you could put in new bats or new blown insulation. If you're keeping the drywall, or you're not planning on ripping any parts of the wall off, you're not going to be able to get into those cavities and fill them with bats. So you can do what's called drill and fill insulation, where just like you see in this photo, they drill holes in every bay and then blow in insulation up to a specific density. And yeah, it can be done with fiberglass or cellulose. You do have to consider that you'll need to patch the drywall and repaint it and finish that. Sometimes this is done from the outside, particularly in occupied buildings. If the owner doesn't want to have to go into every single apartment and then deal with repainting walls, they'll do it from the outside. But if you do it from the outside, you have to think about, you'll have to patch the stucco or otherwise patch the siding. And you'll also have to think about making sure that all those openings are watertight, because you've now introduced a hole into the outside of your building. So there are trade-offs either way. If we're dealing with concrete or masonry walls, insulating these can be really challenging, but the ideal location for insulation is on the outside of those walls. So let's talk a little bit more about insulating on the outside. If we can, it can be really beneficial to insulate on the exterior. And the reason why is building science. Insulating on the exterior improves the continuity of our insulation and reduces thermal bridging. If you look at this picture here, these pieces here, these are just furring strips. The insulation is totally continuous along this entire surface. So you don't have any framing breaking up the insulation and causing thermal bridging. You have a continuous layer of insulation. So you get sort of much closer to the rated R value of your insulation if you can do it continuously on the outside. So it only really makes sense to do this if you're replacing the sheathing or the siding, because you have to put it up and then cover it. The materials for this, the best are rock or stone wool, because it's fireproof, has low embodied carbon, and it doesn't care about getting wet. It can get wet and it's totally fine, no problem. The water will drain out, it'll dry, it's fine. An acceptable product that can be used in these applications is foam. It's pretty common and it's pretty cheap, but foam does contain fire retardants, and it has very high embodied carbon. So if you're concerned about reducing the environmental impact of your buildings and you want to be more efficient, we should think about what's the energy and the greenhouse gas emissions that are generated just by building the products that are going into our building. And foam has a really high embodied carbon. So it's just something to keep in mind when you're thinking about selecting insulation materials. So that's it on insulation. Are there any questions?
Yeah, we had one question about the blown-in insulation in the attic spaces. So if you already
Yeah.
have blown-in insulation in the attic space, is it better to remove that insulation or blow in on top of it?
Yeah, that's a good question. If you suspect that there may be areas of significant air leakage, those will be much easier to seal if you remove the existing insulation. You'll then be able to get to things to deal with sealing any leaks or cracks or openings. If you are fairly confident that there's not any air leakage, you could just insulate on top of the existing insulation. But we generally recommend, when possible, to remove the old stuff, do a really nice job of air sealing your attic so it's nice and tight, and then re-insulate on top of it.
Yeah, great. I think that's a very good point about the insulation or the air sealing under the insulation.
Yeah, and if you're
But
trying to figure out if you have air leakage in an attic, you can look for spots where the insulation is dirty. So if I saw like a bunch of dirt like around here or around like an edge, that would tell me that my insulation is acting like an air filter. Air is moving through the insulation in that location, and so I have air leakage somewhere. So if you go up there, I mean, there's going to be sort of like bits and pieces of stuff that kind of fall off the roof. That's kind of that's pretty common. But if you see any area where like, whoa, it's really dirty right here for no reason, the reason is that air is either coming out or going in to the building through that location. You probably have air leakage.
Yeah, and to add just another point on top of that, which is common in new construction, if you can do a blackout or brownout test where you have all of the lights off in the attic space and you look for light poking through from the from the conditioned area, there's an air leak there or a potential air leak there.
Definitely, definitely.
So that's all the questions we have for now.
Okay. All right. So let's move on to windows. Windows are a very popular measure. They really can improve the feel of a unit, and they can have a pretty positive impact on energy. Usually not as big of an impact as people might think they have, and certainly not as much of an impact usually as doing something in the attic or the walls. But they are an important component of our envelope. And they're a beautiful component of our envelope because they allow us to see outside. Everybody loves windows. So when we're looking at window materials for our projects, we have sort of two things to think about at a very basic level: the frame materials and the glazing itself, or the glass. So for our frames, it's best to choose non-conducting materials like fiberglass, wood, or vinyl. These are going to be the most insulating versions of windows that we can get. So they're going to not conduct heat from inside to outside or vice versa, and you won't have sort of cold interior window frame temperatures in colder months. If you have to do aluminum, for example, on like a mid or high-rise multifamily building, and you have to do aluminum for specific reasons, it's really important to specify thermally broken aluminum. It doesn't perform very well compared to non-conductive materials. You can get okay thermally broken aluminum frames, but they're never going to be as good as a window frame that's made with a non-conducting material. One location where even um, sort of low to mid-rise projects might still have aluminum windows is in any storefront location. Storefront is almost exclusively aluminum, and so it's really important when you're looking at your storefront that you're doing it with thermally broken frames and trying to get the performance of that frame as good as possible. So once you know what kind of frame you have, you want to select your glazing. So the standard practice at this point is double pane low E or low emissivity glazing. The low E coating is what gives windows their sort of greenish or bluish tint, and it's actually a thin layer of metal, of a variety of metals. And what it does is it reduces the amount of solar heat gain that, once absorbed by the window, is radiated into the building. And so you can still get visible light coming through, but instead of radiating that heat right into the building, the window will just hold the heat and not radiate it into the building. So you don't get as much overheating in the summer. So that's standard, double pane low E. Higher performance window would be a triple pane window. So triple pane windows are the kinds of windows you see in much colder climates or in very high performance buildings like passive house projects. And coming soon, something that we're really excited about is something called a thin triple. So it's what you see on the right-hand side of this slide. And it's a triple pane window where the middle pane is a very thin, non-structural glass. So that middle pane is not doing anything to hold the window together, and it doesn't have any real strength. All of that is being carried by the outer two panes. But adding that third layer in the middle really significantly improves the thermal performance of the window. And because it's thin, you can fit these windows in a standard frame. So you don't have to change all of your details. You can still do all of your same install practices, but you can get much higher performance out of your window. We're starting to see these on a few projects. So if you're interested, we can try to provide you with some more information. I haven't personally seen them on a project yet, but it's a very hot topic in the window space right now, and we're very excited for the potential of these. So that's it on Windows. It's a big topic, but we only have really sort of one slide about it. A few things to keep in mind on Windows is that the performance of your windows can impact your heating and cooling loads in different ways. So there are two main performance numbers for a window. There's the U factor and the solar heat gain coefficient. The U factor is essentially how conductive is the window. So a lower U factor means it's less conductive, and that's what you want. So you want a very low U factor. So a U value of like 0.3 is pretty standard. That's pretty easy to get a 0.3 U factor window. You start to get higher performance when you're down into the like mid 0.2s, maybe around 0.2, 0.18. Some triple pane windows can get down to like 0.12, which is an extremely high performance window. The other performance value you'll see is the solar heat gain coefficient, which we mentioned, SHGC. Sort of a standard value for those is around 0.25 or so. If you want to really limit your solar heat gain, you can get those down to 0.2, 0.15, 0.18 in that range. That'll really, it doesn't have to reduce the amount of visible light coming through, so you still get light coming into your building. You just don't get as much heat gain coming in through your building. And especially as we move to buildings that are better air sealed, that have better insulation, it may have been that in the past we wanted a lot of that free heat from the sun because it helped heat our buildings and it sort of reduced the amount that we needed to run our heating system, particularly in mild to cold heating dominated climates like we have here on the West Coast. However, as our buildings get tighter and get better insulated, all of a sudden we don't need to run our heating system nearly as much. And in fact, there are going to be times when we are generating enough heat inside the building just through our bodies, through our appliances, through all of the various heat gains that we have inside a building, that we don't want that extra heat from the sun. And especially for projects that may not have air conditioning in coastal climates, we would strongly recommend going with a low solar heat gain coefficient to avoid overheating. And if you have air conditioning, you definitely want a low solar heat gain coefficient so that you're not increasing your air conditioning loads. So sort of for everyone, unless you're in a super cold Arctic climate, I would say go low on the solar heat gain coefficient. And then definitely for everyone, go low on the U factor. A low U factor is always going to be better. In terms of performance value on different orientations, some folks go to the level of selecting a different solar heat gain coefficient on, let's say, east and west sides versus on north and south. It's definitely something you can do. It tends to make a project more complicated, but it is the case that on the east and west sides of a building, you get sun at a lower angle. So you're going to get more direct sunlight coming in through your east and west sides. And maybe the orientation of your site means you're just going to have a ton of windows that are going to face southwest. In that case, and I actually have a project like this, they weren't able to shade the windows, and there were a lot of units that just faced southwest. And we were like, whoa, guys, this is going to be a big overheating risk. So they specified very low solar heat gain coefficient on those windows to try to keep as much of that solar heat out. So yeah, windows are an important component of your envelope, and how you select them it depends on your climate, but there's some basic ideas. Low solar heat gain coefficient, low U factor, that can work for just about everybody. Are there questions on Windows? Whoops, this is kind of out of, anyway, we don't have a question slide here, but are there questions on Windows?
There are no questions in the question box as of now.
All right, so continuing on, so we've built tight. We've done things that are gonna make our envelope tighter. We've done air sealing, then we've insulated, we've improved our windows. So now we have a nice tight building, and so we need to make sure that it's well ventilated, right? So with a tighter envelope, we have to be very careful to provide adequate ventilation. And I want to emphasize that ventilating right means providing enough, but not too much fresh air. So moving from left to right in the middle of this slide, we have a few approaches to ventilation in multifamily buildings. We have so-called natural ventilation. And I really like to emphasize that natural ventilation is really just random and unreliable ventilation. You have no way to control precisely flow rates in a naturally, I'm making air quotes with my fingers, you can't see it, but a naturally ventilated building just means I don't really know how much ventilation I'm getting. Maybe I'm getting a lot, maybe I'm not getting very much. In order to have, so even if I open a window or I open multiple windows in a naturally ventilated building, I need to have one of two things to get any airflow at all. I need to have a difference in temperature between inside and outside, or I need to have a difference in pressure inside and outside. If I have one or the other, I will get some airflow. And if I have neither, I will get no airflow. So for example, on a very cold day or a very hot day, if I have a large difference in temperature between inside and outside and I open a window, I'll get a lot of airflow. Great. Maybe it's more airflow than I want, but I'll get some. On a very nice day, where let's say it's about the same temperature inside and outside and it's pretty calm, there's not really any wind outside, so there's not much pressure difference, I might not get very much airflow at all. So I can't emphasize enough that naturally ventilated buildings, it sounds like a great idea, but you have essentially no control over how air is moving in and out of your buildings. And it's very crude, and it really can't reliably deliver air quality and comfort for residents. So recognizing this, for a while now, we have been putting intermittent exhaust ventilation in our buildings, usually at the bath and kitchen. And how does the air that we're exhausting all this air out of the kitchen and bathroom, how does air come back into the building? For the most part, we have no idea. It is passive. It just sort of comes in however it comes in. I don't know very many people who, whenever they go to the bathroom or turn on their kitchen hood, always open a window. Does everyone do that? Probably not. Most people leave their home or their apartment however it is, and then they use their kitchen fan or they use the bathroom and the bath fan comes on. So the air that's coming in to make up for the air that's being exhausted comes in kind of wherever. And sometimes it might be coming through a space that we'd rather it not. Especially with crawl spaces, we often see a lot of makeup air coming through the crawl space. And if you spent any time in crawl spaces, that might not be what you'd like your supply air to come through. So an improved ventilation approach to this exhaust only with passive makeup air would be to actually provide filtered supply air. So filtered at MERV 8 or MERV 13 levels, in addition to exhaust air. So you're providing filtered fresh air and you're exhausting air from those areas like the kitchen and the bathroom that can have a lot of moisture buildup. And so this provides a more balanced ventilation approach, and you know where your supply air is coming from. So the first one, you had no control. You didn't know where it was coming from. The second one, you had some control. You knew how much ventilation you were getting. You didn't know where it was coming from. And you don't know if it's clean or dirty. If you have allergies, you're just kind of out of luck because you're getting whatever air you're getting. But the third one, now we are controlling the flow rate and we are controlling the air that's coming in by filtering it. Now, on a building with this kind of ventilation, you can still open a window if you want to. But let's say it's a really hot day or it's a really cold day or the air quality outside is really bad. Here in Northern California, we are experiencing, unfortunately, a lot of wildfires on a not infrequent basis. And there are days when the air quality is just really bad. And if we are building housing and telling people that to ventilate their apartment, they need to open the windows, what does that mean for people during a wildfire situation with unhealthy air quality outside? Or what does that mean for folks with allergies? I really think we should think twice before looking at natural ventilation or even unfiltered ventilation as an appropriate strategy going forward. So we can do improved ventilation with filtered supply air and with controlled exhaust to provide a sort of more predictable, higher quality ventilation scenario for our residents. And then as a step beyond that, we have a high performance ventilation approach where we do balanced and filtered supply air and exhaust with heat or energy recovery and summer bypass. So that was a lot of words. So what we're doing is we're using a heat recovery ventilation system that has supply air and exhaust air passing through a heat exchanger so that in the winter you're keeping most of the heat in. So your exhaust air is giving that heat to the supply air, so you're keeping most of it in, and vice versa. In the summer, you're keeping the heat out. But for those times when it might be kind of pleasantly cool outside, let's say it's in the mid 60s outside and you'd like to just bring in that outside air, you don't want to do heat recovery. If you have a heat recovery ventilation system with summer bypass, it allows you to get that free cooling from the outside air, bypass the heat exchanger and still filter your air, but not pass it through the heat exchanger. It's sort of like if you're familiar with commercial HVAC, it's similar to the idea of an economizer, getting free cooling from ventilation air. So again, ventilating right means providing enough but not too much fresh air. If we provide more air than we really need, especially in the winter, it can really make our spaces and our homes much drier than is comfortable. If you have a hot, humid summer, overventilating can make it much more humid and increase your dehumidification loads that you have to deal with in your building. So we need ventilation. People need to breathe, obviously, but it's the kind of thing that we want to do the right amount of. It's a real Goldilocks scenario. If you do too much, you introduce problems. If you don't do enough, you introduce problems. So it's really important to work closely with your mechanical designer to make sure that you're delivering an appropriate amount of ventilation for your building. And the good news is that we have an upcoming training on high performance ventilation. So on Thursday, February 20th, I think Matthew mentioned this earlier, we're going to have a webinar where we talk exclusively about ventilation, and we go into all the different ways that you can improve the ventilation in your projects, both new and existing. And we'll look at examples and talk about equipment and design and layout and all that kind of stuff. So if you're interested in more information about ventilation, we will have it in February. So those are the basic components of our envelope. We have all the things that air seal and insulate and keep things where we want them to be. And then once we do all of that, we need to make sure we provide adequate ventilation, because we're not just going to be assuming our building is leaky anymore. But how do we truly push the envelope? There are a few approaches that are being worked on right now that are pretty exciting for envelope retrofits. There are some deep energy retrofits that are being done in a few different places around the world, based around the concept of what's called energy sprung, which is a Dutch-inspired approach for affordable deep energy retrofits. And so what you're looking at here in the middle is an example of a row house that has gone through the energy sprung upgrade. So on the left, you have what the old ones look like, and in the middle, you have the upgraded one. So they have an upgraded envelope, upgraded windows, and we'll see some examples of other stuff that they have on these. So in the main photo, you can see the before on the right and the after on the left. And what you may notice on the left is that they, one, don't have chimneys anymore. Chimneys are horrendously leaky. So they replaced the chimneys with, it looks like skylights, which is great. Everybody got solar PV, which is also great. Everyone got continuous exterior insulation on the building. And you see those boxes out front. Those boxes next to the front door is an exterior mechanical room that houses heating, cooling, domestic hot water, and heat recovery ventilation in a single box. And it's sort of like a bolt-on solution to give you super high performance mechanical systems as a complete package. You can see over here on the right just how insulating the new envelope attachment is. So you've got the new exterior wall put over the old one. So this is being done not just in the Netherlands, but actually in a few different places around the world. In Europe, they have versions of this program either in operation or being launched in the UK, Germany, Netherlands, France, and Italy. And it is coming to the United States. There are pilot versions of this being done in New York and California. And there is an effort that is just getting underway with the U.S. Department of Energy to bring this nationwide. So there are some real potential opportunities for doing these deep energy retrofits in existing buildings and trying to figure out a model of this that's cost effective and that's market appropriate for the types of buildings that we have in the U.S. And it's likely going to end up being a regional solution because building vernacular is so different from region to region, right? Like buildings in Buffalo, New York look very different from buildings in San Diego or in, Tempe, Arizona, or in Fort Worth, Texas, or, Detroit, Michigan. So it may end up being a regional sort of type of program in the U.S., but there are some really interesting developments happening around this. So if you're interested, you can just go to the Energy Sprung website and look at those links we've provided here. And if you're interested in the U.S. program, or the one on the West Coast, actually, it's called Realize, and it's being run by the Rocky Mountain Institute. So if you look for RMI or Rocky Mountain Institute Realize, you'll find a link to that. And my organization, AEA, is actually a part of the California Realize team. So we're very excited to be working on this. So that wraps up our presentation on pushing the envelope in existing multifamily. I'm happy to take any remaining questions that there might be. We have a bit of time.
Yeah, we made pretty good time with that. Currently, there are no questions in the question box, but if anybody has a question, please submit it to the question box, or if you want to speak, just raise your hand in the GoToWebinar window and I can unmute you. Well, I don't see anything coming in at the moment. So thank you, Nick. This is a really great topic. And if we have any follow-up questions, I'll be sure to send them your way. But I'm happy to hang out on the webinar for a few minutes longer, just in case anybody else has a question pop into their head. But yeah, thank you again.
Yeah, thank you.
All right, with that, I'm going to end the webinar as there's no more questions. We'll see you again in January. Thanks.